All right, welcome to the Explainer. Today, we're diving into some fantastic research material from Dr. Sudheendra S G to really get our heads around the absolute foundation of our digital world. For anyone teaching or even just trying to understand computers, this is ground zero. We're talking about the integrated circuit. So Dr. G's material kicks things off with this really powerful problem. See, early computers like the famous ENIAC were absolute monsters. We're talking almost 17,000 vacuum tubes and, get this, 5 million hand-soldered joints. Can you even imagine? The push for more power meant more parts, more wires, and, of course, more places for things to go wrong. This spiral of complexity was becoming a nightmare, a problem engineers perfectly named the tyranny of numbers. And this, right here, shows you the problem perfectly. On one side, a chaotic rat's nest of wires where every single connection was a potential failure. On the other side, clean, orderly, and elegant. That one little black square on the modern board, that is the solution that beat the tyranny. It's the idea that changed absolutely everything. So the big question is, how did they pull it off? How did engineers break out of this trap where making things more powerful just made them more, fragile? The answer was a revolutionary concept that Dr. G's material nails as a way to package complexity. That solution was the integrated circuit. The core idea was just brilliant in its simplicity. Instead of soldering together thousands of individual parts one by one, an integrated circuit, or IC, built all of them, the transistors, the resistors, everything, together as one single solid block of silicon. That whole mess of wires becomes a simple, super reliable building block. It's like they stopped trying to wire up every single tiny brick by hand, and instead, they started manufacturing with these perfect, pre-built Lego blocks. Okay, so that brings up a pretty obvious question, right? If you can't build it by hand, how in the world do you build something with millions or even billions of parts that are so small you can't even see them? The answer is a process that is itself a total engineering marvel. It's a kind of microscopic printing called photolithography. The process is basically like a copy and paste, but for atoms. You start with this perfectly pure silicon wafer. Then you use light to expose a pattern onto it. After that, you etch away material to create all the little features. Then you dope different areas to change how they conduct electricity. And finally, you add metal layers to connect it all together. You just pattern, etch, and repeat, building up incredible complexity layer by tiny layer. So this incredible new power, the ability to literally print microscopic circuits, it didn't just solve that old tyranny of numbers problem. No, it kicked off something way bigger. It unleashed an unprecedented golden age of growth, a predictable exponential explosion in computing power that would define the tech industry for the next 50 years. Just look at these numbers from Dr. G's research. They're just wild. The first commercial microprocessor in 1971 had about 2,300 transistors. By 1990, we hit 1 million. By 2010, 1 billion. And today, we're talking tens of billions of transistors on a single chip in the phone in your pocket. The scale is it's almost impossible to wrap your head around. And what's really wild is that this insane pace actually became predictable. Back in 1965, Gordon Moore noticed that the number of transistors you could fit on a chip was doubling about every 2 years. This became famous as Moore's Law. And here's a super important point, especially if you're teaching this stuff. Moore's Law isn't a law of physics, not at all. It was more like a self-fulfilling prophecy, an economic target that the entire industry rallied around to hit year after year. And this relentless doubling? Well, it unleashed this amazing cascade of benefits that are really the key takeaways here. First up, size. As you cram more and more transistors in, everything just gets microscopically smaller. And that smaller size, it leads directly to benefit number 2, speed. It makes sense, right? Electricity has less distance to travel, so things happen faster, a lot faster. Which, of course, brings us to the third big win, efficiency. Those tiny switches need less juice to flip on and off. That's what makes the powerful computer in your pocket even possible in the first place. And then, the final piece of the puzzle, the economic knockout punch, cost. When you can print billions of things at once, the cost for each one just plummets. And that's it. That's what made technology available to basically everyone. Smaller, faster, more efficient, and cheaper. That was the magic formula that powered the entire digital revolution. But you know how it goes. This incredible party couldn't last forever. As engineers kept pushing, making things smaller and smaller, they started bumping up against the hard limits of the universe. The laws of physics, well, they started to push back. So the first big roadblock Dr. G's material points out actually came from the manufacturing process itself, photolithography. Think about it like this. Try drawing a super fine, delicate line with a thick, clumsy marker. At some point, your tool is just too big for what you're trying to draw. The same thing started happening with light. The circuit features were becoming smaller than the very wavelength of light used to print them. The second limit is, well, it's even weirder. It's where we get into the strange world of quantum physics. When you make the insulating walls inside a transistor just a few atoms thick, electrons start to cheat. They can do this thing called quantum tunneling, which basically means they can pop right through a solid barrier as if it wasn't even there. And when that happens, you get errors. The transistor just doesn't work right anymore. So is that the end of the line? Is progress just over? Not even close. As the source material shows us, the end of one road is just the start of a whole new adventure. Engineers are already way into the next chapter, coming up with all sorts of clever new tricks to keep things moving forward. And this has sparked some truly incredible new ideas. Instead of just shrinking things on a flat surface, we're not building up, stacking chips vertically, like little skyscrapers of silicon. Or we're using these modular chiplets, kind of like Lego again, combining smaller, specialized chips together. We're even redesigning the whole transistor, moving from flat 2D gates to these amazing 3D structures called FinFETs that give us way better control. See, the innovation isn't about just shrinking anymore, it's about getting smarter with design. And that really brings us to the big takeaway here. The old, simple roadmap of doubling every 2 years, yeah, that might be changing. But that human drive, that spark of ingenuity to solve the next impossible problem, that is as strong as it has ever been. So it leaves you with this really cool thought. The law might be fading, but the spirit of innovation it created is just getting started on its next, and maybe even more fascinating, chapter.